Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. One of the things that I said I wanted to do when I started Trig on Tuesday was to go over the astronomy and mathematics of the ancient Greeks. So today we're going to start a sub-series on the astronomy of the ancient Greeks and how they determined the size and distance to the sun, the moon, and the size of the earth. Now we're going to use the classical proofs of Aristarchus of Samos. And I want to credit Physics Explained to doing this originally a couple of years ago. I did feel that he skipped a few steps, and I thought by adding those steps I would add some clarity to this, so I've decided to remake it. But the original idea came from Physics Explained. Now let's see what we're going to do. We're going to use observations of the half moon to determine the distance from the Earth to the Sun in terms of the distance from the Earth to the Moon. And then we're going to look at a solar eclipse to determine the size of the sun in terms of the size. A lunar eclipse will help us determine the size of the moon and the sun in terms of the size of the earth. Then we'll look at an observation of the full moon to determine the distance of the sun and the moon to the earth in terms of the diameter of the earth. And then the final step will be to determine the size of the earth by the method of Eratosthenes. So, cue up the music and let's get started. Now, in classic Greek astronomy, there was a series of observations of the Earth and the Moon that were used to determine the distance between the Earth and the Moon, the Earth and the Sun, and the size of the Earth. The first is going to be the observation of the half moon. That will give us the distance to the Sun in terms of the distance to the Moon. During a solar eclipse, we are able to determine the diameter of the sun versus the diameter of the moon. During the lunar eclipse, we obtained two observations. The first is a comparison of the diameter of the sun to the diameter of the earth, and the second is the diameter of the moon in terms of the diameter of the earth. Finally, by observing the full moon, we were able to find the diameter of the moon in terms of the distance to the moon. And then finally, we have the circumference of the Earth based on the experiment of Eratosthenes. So let's go through these one at a time. Now, in the first observation, Aristarchus reasoned that if we saw a half moon from the Earth, that meant that there was a right angle formed on a triangle between the sun, the moon, and the Earth. If we could determine this angle theta, we could determine the distance to the sun in terms of the distance to the moon. And that's a rather straightforward calculation in that cosine theta equals the distance to the moon over the distance to the sun. Angle theta, by modern determinations, is 89.85 degrees. Now, we want to determine the distance to the sun in terms of distance to the moon. We're going to have to invert these equations. So, distance to the sun over the distance to the moon equals 1 over the cosine of 89.85 degrees. Now, just for precision, we'll put in the full modern measurement, which is 89.853 degrees. So, if we go 89.853, take the cosine and invert that, we get approximately 390. The distance to the sun, in terms of the distance to the moon, is approximately 390. Okay, so that was a relatively simple equation, and as a result, we now know that the distance from the Earth to the Sun is approximately 390 times the distance from the Earth to the Moon. Next, let's have a look at the solar eclipse to get an idea of what the size of the sun versus the size of the moon would be. For our next calculation, we need to go ahead and have a look at the concept of similar triangles. So if we have a right triangle, like so, and we draw a second right triangle within it, angle alpha will be the same for both triangles. These will both be right angles, and this angle will be the same as that angle. So by definition, these triangles are what is called similar, which means that even though the sides are of different length, all three angles are exactly the same. And we're going to use that concept to use the solar eclipse to look at the diameter of the sun compared to the diameter of the moon. Let's identify the diagram here. Here we have the radius of the Earth. Here we have the radius of the moon. And out here, of course, we have the radius of the sun. This entire distance is the distance from the Earth to the sun. And this distance is the distance from the Earth to the moon. So we have two similar triangles here. We have one formed by the radius of the sun and the distance from the Earth to the sun. And we have a second one formed by the radius of the moon and the distance from the Earth to the moon. Because these are similar triangles, we realize that the distance to the sun over the distance to the moon equals the radius of the sun over the radius of the moon. And since the radius is simply half the diameter, we can also say that it's the diameter of the sun over the diameter of the moon. These are all equivalent terms because we're comparing similar triangles. Now this makes the answer rather simple because we have just determined that the distance to the sun over the distance to the moon equals 390. So it follows that the radius of the sun over the radius of the moon and the diameter of the sun and the diameter of the moon also equal 390. Well, that was pretty straightforward, wasn't it? The distance to the sun over the distance to the moon is 390. The diameter of the sun over the diameter of the moon is also 390. Now, let's go and use the lunar eclipse to see how we can find the size of the moon and the sun in terms of the size of the Earth, because that's the only thing that we can really measure. So that's what we'll do. Now, going on to the next one, we need to have a look at another concept. Again, this is similar triangles. So if we have a large triangle and we draw a line parallel to the base, these will both be right angles. This angle is shared by both triangles, so it's the same. And by definition, that means that these two angles must also be the same. And as a result, we're going to use that principle to determine the size of the sun versus the size of the Earth, and the size of the moon versus the size of the Earth. Now, this is a little bit more complex than the last one that we did. Now, once again, here is the distance to the sun. Here is the distance from the Earth to the moon. Now, because they're similar triangles, we realize that the distance to the sun over the distance to the moon would equal the height of the triangle formed by the Earth and the sun over the height of the triangle formed between the Earth and the moon. Now, first we have the radius of the sun. However, the height of this triangle is not the radius of the sun. It's the radius of the sun minus the radius of the Earth. This is the radius of the Earth here. Likewise, here we would have the radius of the Earth minus the radius of the shadow cast by the Earth. That's this point right here. One thing that we should note is that the diameter of the shadow of the Earth is about 2.6 times the diameter of the Moon. Okay, so now we need to do a little bit of math. Now, one thing that should be immediately apparent is that we have two similar terms here. So we can rewrite this 1 minus the radius of the Earth over the radius of the Sun equals the radius of the Earth over the radius of the Moon minus the radius of the shadow of the Earth over the radius of the Moon. Now, the next thing that we can do is let's get rid of these negative signs. So let's add this term to the left side, and we'll add this term to the right side. We end up with something that looks like this. Now we're getting someplace because we know that the radius of the shadow of the Earth is about 2.6 times the radius of the Moon. So we can replace this with a number and just get rid of this term. So now we have 1 plus 2.6 equals the radius of the Earth. Now, wait a minute. Before we go much further, let's go ahead and get a common denominator here. So how would we do that? Well, the first thing that we would do is we'd say the radius of the Earth times the radius of the Sun plus the radius of the Earth over the times the radius of the Moon. And we can put both of these over radius of the Moon times the radius of the Sun. Now we're ready to finish this up. Well, let's go ahead and factor a few things here. So let's say that 3.6 equals the radius of the Earth over the radius of the Moon. Okay, what's this first term become then? So we take out the radius of the Earth and the radius of the Moon, and we're just left with the radius of the Sun over the radius of the Sun. That equals 1. Plus, once again, we take out the radius of the Earth, so we have the radius of the Moon. And then we have the radius of the Sun left down here. Now, the next step is a rather simple trick. We want the radius of the Earth over the radius of the Moon because that relates the radius of the Earth to the radius of the Moon. So let's bring it over here. Let's bring this bracketed term over to the other side. So that would be 1 plus the radius of the Moon over the radius of the Sun equals the radius of the Earth over the radius of the Moon. Now, we recall that the radius of the Sun is 390 times the radius of the Moon. So that equals 3.6 divided by 1 plus 1 over 390. That's a very negligible term right there, and this pretty much equals 1. So we can say that the radius of the Earth to the radius of the Moon equals 3.6. You follow through with that? We'll put it right there. Now, we can do exactly the same thing with the radius of the Sun and the radius of the Earth. So, we can pull out the radius of the Earth, and we can pull out the radius of the Sun. So here's A. Let's go down here to B. So 3.6 equals the radius of the Earth over the radius of the Sun times, well, what? We've got the radius of the Earth pulled out here, and we have the radius of the Sun pulled out here, and that leaves the radius of the Sun over the radius of the Moon. Now on the other side, we've pulled out the radius of the Earth and the radius of the Sun. That just leaves the radius of the Moon over the radius of the Moon, which is 1. Now, we bring this around the same way, and we end up with 3.6 over the radius of the Sun to the Moon is 390 plus 1. This is the radius of the Earth to the radius of the Sun. So by flipping this over to get the radius of the Sun over the radius of the Earth, we get 391 over 3.6. And now we can solve for that. So we have 391 divided by 3.6 equals about 109. Well, I don't know about you, but I think this is kind of fun. Well, we have these values up here, and now with the lunar eclipse, we also know that the Sun is 109 times the size of the Earth, and the Earth is 3.6 times the size of the Moon. Let's go on to the final step here, and that is, let's have a look at the full moon. Well, folks, I think that pretty much finishes it up for today. We had a look at 3 principles. The first was the geometry of the ancient Greeks, specifically using similar triangles. The second was a little bit of trig and some algebra. Now in our next episode, we're going to have a look at the full moon and the angular size of the full moon compared to the orbit of the moon. And that'll help us determine the distance to the moon and the sun in terms of the diameter of the Earth. Then we'll use the Eratosthenes experiment to find the diameter of the Earth, and we'll do some calculations. So until then, this is Bob the Science Guy signing out from Northern Michigan. Thank you again for stopping by. Make sure you hit that like and subscribe, and I'll see you again next week.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.